Today we're going to cover Newton's method for nonlinear systems, and we've done Newton's method for just a single function, root finding for a single function. But let's see how this looks in the context of a nonlinear system. Okay, so you can see over there on the left, let me get a pen here. You can see here we have a bunch of equations set equal to 0. So let's say, your equation started off as x squared plus y squared is equal to 9, and how about x squared minus y squared is equal to 1. Okay. Well, what you'd want to do is you'd want to rewrite each one of these by just setting them equal to 0. So your f1 would be equal to x squared plus y squared minus 9, and your f2, your second function, would be x squared minus y squared minus 1. And then you can see in this next line that we say we're going to turn this into a vector valued function. And so what do we mean by that? Is we would mean here that we have some function that you input x, y, okay, and then our outputs are determined by these two functions. So x squared plus y squared minus 9 and x squared minus y squared minus 1. Okay, and so really our goal is to find an xy that satisfied these two original equations. But if we find a pair xy that satisfy both of those equations, then is what we've found is something that makes this 0. Okay? We want to know for what xy does this equal 0. Okay? And that's what this third thing down here is saying. Okay? All right, well, let's move down a little bit further. Okay. So we take our system of equations, we set each equation equal to 0, okay, and then the non-zero side of that equation is the corresponding function. This allows us to create a vector valued function, and then we want to set it equal to 0. Okay. And is what we're going to do from here is we are going to rewrite the function using its linear approximation. Okay. So the linear approximation when we were in 2D was just a tangent line. Here it could be a plane or hyperplane. Okay. And right here, let me put an arrow to it. This is our formula for our linear approximation. Okay. And there's something that we haven't learned about here, and it's called the Jacobian, J here. And you can see it just consists of all the partials of f1 through fn. Okay. And really is what this is doing is this is making sure that if we move a little bit in the x1 direction, that we move up the corresponding amount that we would like vertically. Okay. And as we move in the x2 direction, that we move up by the corresponding amount that would be expected if we moved in that direction, okay, and so on. Okay. All right. And lastly, we're going to take this linear approximation, just like we did with the tangent line. We're going to set it equal to 0, and we're going to solve for x. Okay. Let's go ahead and do that. So the first thing I'm going to do is I'm going to move over this minus f of x naught. One thing to keep in mind is this j of x naught is a matrix. So if we want to move it, we're going to need to multiply by its inverse. Okay. All right, so let's go ahead and do that. Let's multiply by the inverse here. And we want to make make sure that we're left multiplying by the inverse. I just wrote the negative out front. That way we didn't need an extra set of parentheses. Okay. And then over here on this side we have x minus x naught. And our goal was to solve for x here. So we just want to add x naught to each side. So this leaves us with x naught is equal to, x is equal to x naught minus the inverse of the Jacobian times f of x naught. Okay. So there's our formula. And so our code's actually going to look pretty similar to what it looked like when we did Newton's method in the first place. It's just it's vectorized here now. All right, let's go ahead and get this in Matlab. We are in Matlab now, and we are going to call this function newtmult. Okay. And again, make sure to name your file that as well. Let's see what the inputs are. The input is going to be one of them is going to be a function. Okay. And this function will actually be something that gives us our Jacobian and our functions f1 through fn. X naught here. Okay. This is our guess. It should be a vector. Okay. Our guess at where the root is or the solution. And then ES will be our desired relative error. Maximum number of iterations, and then here we have var argin for a variable number of input arguments. Okay, and then down here we have a couple settings here. So we want to report an error if there are less than 2 inputs, because we need at least that function I was describing and a guess. The default for the relative error will be 0.0001, and the default for the maximum number of iterations will be 50. Okay. All right, so let's move on to the function here. We are going to want to count our iterations. That was one of our outputs there up top. So iter equals 0 before we get into our loop. Okay. And then as we update our estimate for the root, okay, or solution, let's call that x. So let's just say x equals x naught here to begin with, but of course x is going to change. Okay. And we'll have while. There we go. While 1. And the first thing that we're going to want to do is we're going to want to produce our Jacobian and this function f, which again will just contain f1, f2, f3, f4, however many functions that we need. Okay. So J will be a matrix, and f will be a vector of functions. And this is going to come from func x var argin okay. And then next we are going to compute let me go ahead and type it here, what we're going to call dx, which will be the Jacobian backslash f. And let's see what that is here in our OneNote. All right, now that we have switched to OneNote, I want to note, let's say we did have the Jacobian matrix, okay, which I'm just going to denote as j here. I'm not going to write the of x naught. Okay, we have our Jacobian matrix, and then we have times some vector. Okay, and let's say that that vector gave us f of x naught. Okay, and let's say we want to solve for dx here. Well, if we did that, we'd have dx equals the inverse of the Jacobian times x naught, or f of x naught. Right? That would be one way to think about dx. Or in Matlab, if we were to solve for dx, we might actually solve that by doing j backslash f of x naught. And so this is what we have in Matlab rather than using this. Okay? And let's go ahead and switch back to Matlab. Okay? All right, here we are. So we had our dx. And so if you remember from the previous page, the next formula was really just x equals x minus dx. Okay? Let's make sure we have everything suppressed here. It looks like dx is the only thing I've left unsuppressed. And let's next count our iterations. Okay, so now that we have reassigned x a value, let's say iter equals iter plus 1. Okay, let's go ahead and also compute our relative error. So EA is equal to 100 times the max. And this is going to be kind of interesting here, the absolute value of dx over x. And let's talk about what's going on here. Okay, so this is our previous x. That's what we're used to having, our current x, and that's what we're used to having in the denominator when we compute our relative error. And then dx is actually just the change in x, which is normally what we put up here. We would normally do, you know, x new minus x old in the numerator, and this dx accounts for that. Okay. So our relative error formula is a little bit more simple than usual. Okay. And then next, if iter, okay, we need our conditions for breaking the while loop. So if iter is greater than or equal to max it, or EA is less than or equal to ES, we want to break. All right, and so this is the whole function, but what I'd like to do next is switch over to a different tab, and we will see how we can actually implement this function. Let's go ahead and save our newtmult function, and let's switch over to this tab here. So this is the example from yesterday that we used when we were talking about successive substitution. Okay. And it's what we found graphically, and then later on using successive substitution, that these were good guesses to start with. Okay. Now, for our newtmult function, the very first input we need is actually a function. Let's call it fun, but we're going to need to go make this function. We're going to need our initial guess here for x naught. And so that should be 1.5, 3.5. And then we can just use the defaults for the rest of that. But now the hard part is going to be making this function here. So let's go ahead and switch tab. All right, now I've created a file, fun. Okay. So this is going to be our function. And so we're going to need to compute two things here. One is f, and the other one is the Jacobian. Okay. And so remember, to come up with these functions, all we need to do is write out each equation but set equal to 0. So how about x of 1 squared, and then plus x of 1 times x of 2, okay, and then minus 10. Okay, so there's our first function. And then our second one should be x of 2 plus 3 times x of 1 times x of 2 squared, and then minus 57. Okay. And let me just double check what I have here. All right, that all looks good. Let's go ahead and fill in our Jacobian. So we want to start off in the first row by looking at the partial derivatives of the first function, and the second row will be the partial derivatives of the second function. So if we take the derivative of this first function here, and with respect to x1, we should get a 2 times x of 1 to the 1 plus, okay, plus, and now if we differentiate with respect to x1 for this term, that means this x of 2 is going to get treated as a constant, so we'll have plus x of 2. And then the derivative of this with respect to x1 will be 0. So there is our first partial. Let's now take the partial with respect to x2. So this is all constant, so that'll go away. And if we take this next term, its derivative with respect to x2, we're just going to be left with x1. So that's x of 1. And then the derivative of this here is just going to be 0. Okay, so we'll move on to the next line, and we'll start taking the partials of the second function. So if we go with respect to x1, all we're going to be left with is this 3 here that's attached to the x1, and this x of 2 squared. Okay. So 3 times x of 2 squared. Okay. Again, that was our partial with respect to x1. Everything else was constant and is gone. And so next we want to take our partial with respect to x2, so we should have a 1 plus, this 2 right here is going to come down, so it's going to be plus a 6 times, that's not a 6, there we go, 6 times x of 1 times x of 2. All right, so there is our Jacobian. All right. Let's go ahead and save this, and we'll switch back and we'll test this all out. Okay, but again, all we did in here is we made a function that outputs our Jacobian and our f's. Okay, let's go ahead and switch over here. Now, fun here, I want to actually be treating this as a function. There we go. So we have our function here now, and we have our input. Let's test it out. Okay. Remember, the answer should be 2, 3. Let's see what happened. There it is, 2, 3. And it looks like I left something unsuppressed in our Newt-Molt function. Or actually, I think that that's from our fun here. Yeah, I didn't suppress f. So now if I save this and rerun it, hopefully we'll see a few less outputs. All right, and yeah, that's it, just the 2 and the 3.